Hey, we will deal with a real-life example about car sales. Actually, it is so real-life that it is very messy, and we will need to first clean our dataset, then go through several assumptions, relax some of them, practice the concept of log transformation we mentioned earlier, create a model, and eventually we will finish off with some dummy variables. I bet you will be blown away by all the things you already know. Everything will be interconnected, so get comfortable and let's start analyzing. Our dataset is in the file 1.04, real-life example. So I'll load the CSV in the variable raw data. Here's our dataset. This is a list of second-hand cars with their respective price, type of body, mileage, engine volume, engine type, year of production, model, and information about the time when they were registered. What we would like to do is predict the price of a used car, depending on its specifications. The first potential regressor is brand, as it is well known that a BMW is generally more expensive than a Toyota. The second relevant variable is mileage, since the more a car is driven, the cheaper it should be. Third, the engine volume. Sports cars have larger engines and economy cars have smaller engines. And the final variable is year of production. The older the car, the cheaper it is, with the exception of vintage vehicles. The rest are categorical variables, which we'll deal with on a case-by-case basis. All right, we haven't spoken about data cleaning so far in this course. So far, all datasets were cleaned before being presented. This time it will be different, and you will get a feeling of how raw data looks like. An easy way to check your data and spot problems is to use the descriptive statistics as we did earlier. So, that's what I'll do. The relevant method was the data frame dot describe. Notice that we only got descriptives for numerical variables. That's what we obtain by default. I'll adjust that with the argument include equals all. That's more like it. Now we have descriptives for the categorical variables too. Great! First thing we notice is that each variable has a different number of observations, which implies there are some missing values. Next, we can see unique entries for categorical variables. There are 312 unique models. That's something really hard to implement at a regression. That would mean more than 300 dummies. Another piece of information we obtain is the most common category. Below is its frequency. Registration, for instance, has 3,947 yes entries. Almost all of them. Looks like this variable won't be very useful. As we mentioned, reliably implementing model into a regression would be a very hard task, so we'll drop the variable. A lot of the information from model could be engineered from brand, year, and engine volume, so we won't be losing too much variability. Once we are done with this practical example, you can try running a regression with model too. To remove the variable, we'll use the pandas method, drop. It has two arguments, the columns I want to drop and the axis. Remember that axis 0 means rows, while axis 1 stands for columns. I am dropping columns, so axis equals 1. Good. Let's examine what's left in terms of variables. Now, we still haven't addressed the missing values problem. Brand, body, mileage, registration, and year seem to have no missing values given that the total number of observations is 4,345. We can't say the same thing about price and engine volume, though. An easy way to check for missing values is to write data.isNull. It shows us a data frame with that information. True stands for a missing value, while false for an available one. Since true is basically 1, while false is 0, we can write isNull.sum. This method will sum all the missing values and give us the number of null observations. Price and engine volume are the only features with missing values, but only several of them. Therefore, I'll simply delete those observations. A rule of thumb is that if you are removing less than 5% of the observations, You are free to just remove all observations that have missing values. In this case, they are less than that, so we are safe. The easiest way to remove them is with the ad hoc method, dataframe.dropNA. This time, I'll be dropping observations, not columns. So, the axis is 0. I'll put all that in the variable data underscore no missing values, or no MV. Great! Let's see what other problems may occur. I'll print the descriptives once again. Notice the minimum and maximum values with respect to the mean and the quartiles for each variable. Moreover, I'll print the probability distribution functions for each feature as we discuss them. It is fairly easy to do that with Seaborn. We can write SNS dist plot and in brackets, the feature of interest. To plot price, I'll put data no MV price. For the optimal results, we would be looking for a normal distribution. Price, however, has an exponential one. This will surely be a problem for our regression. What about its descriptives? Price has a mean around $19,000. The minimum price is $600. 25% of prices are under $7,000, 50% below $11,500, and 75% are lower than $21,900. Yet the maximum price is $300,000. Something strange is going on. Obviously, we have a few outliers in the price variable. Outliers are observations that lie on abnormal distance from other observations in the data. They will affect the regression dramatically and cause coefficients to be inflated, as the regression will try to place the line closer to those values. One way to deal with that seamlessly is to remove the top 1% of observations. The simplest way to do that with code is through the quantile method. It takes one argument, the quantile. You can input values from 0 to 1. If you input 0.25, you will get the 25th percentile. I want to get the 99th percentile and keep the data below the 99th percentile. This is one way to eliminate outliers. Okay, what's a smart way to do that? We can declare a new variable called Q. It is equal to data no MV, price series, dot, quantile 0.99 in brackets. By the way, this is actually a value, around $130,000 actually. Next, I will simply create a new data frame where we will keep only those entries of price, which are lower than the 99th percentile value. Notice that this code is extremely reusable. Great! Let's see the descriptives now. Amazing! The maximum value is around $130,000, or the 99th percentile. While still far away from the mean, it is acceptably closer. Note that in general, we don't print descriptives in data frames all the time. You do it once and just manipulate your data with code until you are done. Every now and then, you can check what's going on, but you'll rarely do that later when you become more experienced. What about the PDF? It is confirming what we observe from the descriptive statistics alone. The data is still distributed in the same way, but with less outliers. Okay, this issue is out of the way. However, we have a similar issue with mileage, engine volume, and year. We can see that the situation with mileage is almost identical from its PDF. Therefore, we can deal with it in the same way, by keeping only the data lower than the 99th percentile. Here's the improved result. Okay, easy. What about engine volume? Here's its PDF. It is rather strange. If we were to examine engine volume manually, we will notice that there are also the engine volume values of 99.99, 90, 75, etc. I'm no car expert, but these are not usual values. Moreover, looking at the descriptives, it seems that most values are really low. A quick search on Google would confirm that the interval where engine volume should fall is between 0.6 and 6.5. Therefore, those 99.99s, 90s, and so on are incorrect entries. Actually, a common way to label missing values is by assigning 99.99. That's something that stuck from the early ages of computers. It is a bad idea to label values in such ways, as it is very hard for other users of the data to distinguish them from the true values. However, be aware that some people still do it. Here we have a benchmark, 6.5. This time, I'll remove all values that are lower than 6.5, as I know the natural domain of the engine volume values. Great! What about year? The problem with year is it's on the low end. Most cars are newer, but there seem to be a few vintage cars. This time, I'll take the first percentile, and then we'll keep all observations that are higher. We will finish off by creating a data variable, and we will reset the index. I'll call this variable data cleaned, as we have successfully cleaned it. Currently, the indices of the data frame refer to all the data, but we want them to describe only the data useful for analysis. The method we will use for resetting the index is dataframe.resetIndex. We will include an argument drop equals true to completely forget the old index. Finally, I'll print the descriptive statistics once more. Now all the minimums and maximums seem about right. Overall, we've deleted around 250 observations, but they were the problematic ones, I promise you that. Enough pre-processing. In the next lecture, we will check and relax some assumptions. Thanks for watching.